Tonight, I want you to do something that will permanently change how you see reality. Step outside, tilt your head back, look up at that dark, quiet sky scattered with tiny pinpoints of light. It feels natural, it feels peaceful, it feels like everything makes sense. But I need to warn you, what you're about to learn will make that peaceful feeling disappear forever, because that dark sky above your head is one of the biggest unsolved mysteries in all of science, and it has been silently screaming at us for centuries. Here's the problem. The classical model of the universe that dominated scientific thinking for hundreds of years, the one championed by brilliant minds, including Isaac Newton, described the cosmos as infinite, eternal, and completely still. An endless ocean of stars stretching in every direction without a boundary, without a beginning, and without an end. At first glance, that sounds reasonable. After all, if the universe has an edge, what's on the other side? The only logical conclusion seemed to be that space goes on forever. But that assumption carries a devastating consequence that almost nobody talks about. If the universe truly contains an infinite number of stars spread across infinite space, then every single line of sight leaving your eyes, no matter the direction, must eventually land on the surface of a star. Not some of them, all of them. The entire sky, every square millimeter of that dome above your head, should be burning with the combined brilliance of countless suns. There should be no darkness, there should be no night. The sky should be a wall of blinding, relentless fire. And yet, you look up and see black. That contradiction has a name. Scientists call it Olbers' paradox, named after the astronomer Heinrich Olbers, who formally described it in the 19th century, though the puzzle itself is far older. And it is not a minor technical glitch in our understanding. It is a fundamental crack running through the foundation of classical physics, a flaw so profound that it forces us to rethink everything we believe about the size, age, and nature of the universe itself. To really feel the weight of this paradox, consider a simple mental image. Imagine you are standing in the middle of a forest, a dense, thick forest packed with trees in every direction. If the forest is small, you can find gaps between the trunks. You can see light breaking through, sky appearing at the edges, open space somewhere in the distance. But now imagine that forest has no edge. It stretches infinitely in every direction. In that case, no matter where you look, your line of sight will eventually hit the bark of a tree. The entire world around you becomes a solid wall of wood. There are no gaps, no openings, no escape. Replace the trees with stars, and that is precisely the mathematical situation we are dealing with. An infinite universe packed uniformly with stars should produce a sky that looks like one continuous blazing surface of light. The geometry is inescapable. The logic is airtight. And yet, when you walk outside at night, none of that happens. The sky is dark, the stars are few, the night is calm. That gap between what classical physics predicts and what your own eyes confirm is not a minor inconsistency. It is a signal, a loud, urgent, unavoidable signal that our most basic assumptions about the cosmos were deeply, fundamentally wrong. And in the next few minutes, we are going to follow that signal all the way down into the strangest and most astonishing truths science has ever uncovered. Now, before we blow apart the classical model entirely, I want to give it a fair defense, because the scientists who believed in an infinite, eternal universe were not fools. They were applying careful logic to the best information available to them. And when the paradox of the dark night sky first surfaced as a serious problem, brilliant thinkers immediately began searching for an escape route. One of the most tempting solutions seemed almost obvious at first. What about dust? Space, as we now know, is not empty. It is filled with vast clouds of gas, dust, and dark material drifting between the stars. Perhaps the argument went, those clouds act as a cosmic curtain. They absorb the light pouring in from distant stars and block it before it ever reaches our eyes. The sky is dark not because the stars are absent, but because a giant, invisible veil of interstellar material is shielding us from their combined glare. Problem solved, except it is not solved at all. And the reason why comes from one of the most unbreakable rules in all of physics, the conservation of energy. Energy cannot simply vanish. It does not disappear when it gets absorbed. It transforms. If those clouds of dust and gas spend an eternity soaking up radiation from an infinite number of stars, they do not stay cold and invisible. They heat up. They absorb more and more energy until they reach the same temperature as the stellar surfaces around them, and then they begin radiating that energy right back outward. The curtain catches fire. The shield becomes another source of light. You cannot hide an infinite amount of energy behind a finite barrier. The barrier eventually becomes part of the problem. So that escape route closes. And we are left staring at the same impossible gap between theory and observation. The universe that classical physics describes should be an eternal furnace. The universe we actually live in is mostly cold and dark. Something is profoundly wrong with the classical picture, and no clever workaround can patch it. The real answer requires something far more radical. It requires us to abandon the idea that the universe is infinite and eternal altogether. And here is where things become genuinely mind-bending. Light, for all its incredible speed, does not travel instantaneously. It takes time to cross space. The light from the sun takes about 8 minutes to reach your eyes. The light from distant stars takes years, centuries, or millennia. And the light from the most remote galaxies we can detect has been traveling for billions of years just to reach our instruments. That fact changes everything. If the universe has a finite age, and modern science tells us it is approximately 13.8 billion years old, then there is a hard boundary on how far light could have traveled since the beginning. We can only see stars and galaxies whose light has had enough time to complete the journey. Everything beyond that cosmic horizon enough times to us, not because it does not exist, but because its light has not arrived yet. We are sitting inside a bubble of observable space, and outside that bubble, the universe may extend much further than we can ever see. This is why the night sky is dark. Not because the universe is small, not because the stars are few, but because time itself acts as a filter, cutting off our view of the cosmic depths and saving us from the inferno that classical logic predicted. The darkness above your head is not emptiness. It is a boundary drawn by the age of the universe itself. And crossing it in your imagination is only the beginning of how strange this story gets. We have established that the universe has a finite age, and that this age is what prevents our sky from burning. But the moment you accept that the universe had a beginning, a completely new set of questions explodes into view, questions that are, in many ways, even more disturbing than the dark sky paradox we started with. If time has a starting point, what caused it? What existed before? And if everything we see emerged from a single initial event, what were the conditions of that event? And do those conditions make any sense at all? Modern cosmology points to the Big Bang as the origin of our universe, an inconceivably hot, dense state from which all matter, energy, space, and time erupted and began expanding outward. The evidence for this event is overwhelming. The expansion of galaxies, the abundance of light elements in the cosmos, and the faint thermal glow that fills the universe in every direction all point unmistakably toward a common, explosive origin roughly 13.8 billion years ago. But here is where the story becomes philosophically dangerous, and where most textbooks quietly look away. The Big Bang is described as a state of enormous heat, density, and chaos particles colliding at tremendous velocities, energy distributed in a wild, turbulent frenzy. In everyday language, we would call that disorder. We would call that chaos. And in physics, chaos has a precise name. We call it high entropy. Now recall the second law of thermodynamics, one of the most universally observed principles in all of science. This law states that entropy, the degree of disorder in a closed system, always increases over time. Drop a porcelain cup and it shatters into pieces. No one has ever watched shards of broken ceramic leap off a floor and reassemble into a cup, because that would mean entropy was decreasing, and entropy never decreases on its own. Time, as we experience it, flows from order toward disorder, always. Apply that principle to the universe as a whole. If entropy increases as time moves forward, then going backward in time means entropy was lower. The further back you trace the history of the cosmos, the more ordered everything had to be. At the very beginning, at the moment of the Big Bang, the universe must have been in an extraordinarily low entropy state. It had to be arranged with exceptional precision, because from that precise starting point, 13.8 billion years of increasing disorder eventually produced the galaxies, stars, planets, and life we observe today. But wait. That contradicts everything we just said about the Big Bang being a hot, chaotic explosion. A raging inferno of subatomic particles crashing together in a compact space sounds like maximum disorder, maximum entropy. How can the beginning of time be simultaneously the most chaotic moment and the most ordered moment? That is not a subtle tension. That is a flat-out contradiction, and it sits at the heart of modern cosmology like a splinter that no one can remove. The resolution to this contradiction requires something that most physicists are deeply reluctant to confront, a rethinking of what we mean by order and disorder when gravity is part of the equation. Because gravity does not play by the same rules as heat and particle collisions. In a gravitational system, the most disordered possible state is not a spreading gas cloud. It is a collapsed singularity, a black hole. And that changes everything about how we understand the beginning of the universe and whether that beginning was truly a beginning at all. To understand why gravity transforms our picture of cosmic order and disorder so dramatically, start with a straightforward observation. In a room full of gas molecules, The most disordered state is when the molecules are spread out evenly, bouncing randomly in all directions. That is high entropy for a gas. But introduce gravity into the equation, and the rules invert entirely. When gravity operates over vast scales of space and time, it pulls matter together. It clumps, it concentrates, it collapses. And the end product of gravity's relentless work is the most extreme object in the known universe, a black hole, a point where matter has been crushed so completely that not even light can escape its pull. A black hole, in gravitational terms, represents maximum entropy. It is the most disordered gravitational state possible. And this means that a universe in which gravity has done its work, a universe full of black holes, is a universe that has aged significantly, moved toward disorder, and exhausted much of its structure. Working backward from this logic, a universe at its beginning must have had gravity in a remarkably ordered state, matter distributed with extraordinary smoothness, no large clumps, no extreme concentrations, no black holes. The early cosmos had to be almost perfectly uniform for the arrow of time to point in the direction we observe it pointing today. And here lies the staggering problem. The mathematics required to produce that level of initial smoothness, that particular starting configuration of matter and energy, is so improbable that describing the number in ordinary terms is practically impossible. Physicist Roger Penrose has calculated that the precision required for the initial low entropy state of the universe is on the order of 1 in 10 raised to the power of 10 raised to the power of 123. That is not merely an astronomically large number. It is a number so vast that if you try to write it out, placing 1 0 on every subatomic particle in the observable universe, you would run out of particles long before you finished writing. To call this a coincidence is to stretch the word beyond any reasonable meaning. Standard cosmology attempts to address this problem through a concept called inflation, the idea that the very early universe underwent an extremely rapid period of expansion that smoothed out any irregularities and produced the uniform distribution we observe. But inflation carries its own difficulties. It requires the introduction of a hypothetical energy field that has never been directly detected, operating under conditions that cannot be tested, and producing a result that is simply assumed as a starting point rather than derived from first principles. Critics argue that inflation does not eliminate the fine-tuning problem. It merely relocates it. There is, however, a different approach, one that does not require invented fields or untestable assumptions. It asks instead whether the beginning of our universe was truly a beginning or whether it was a transition and emergence from something that came before. If the cosmos we inhabit did not spontaneously appear from nothing, but instead arose from the dying remnants of a previous cosmic era, then the extraordinary precision of our starting conditions might not be miraculous at all. It might be inherited. It might be a consequence of physics that operated in that earlier epoch and left its imprint on ours. This is not a casual speculation. It is a framework built on the mathematics of general relativity extended to its most extreme logical conclusions. And it leads to a picture of reality so different from the conventional model that most scientists are uncomfortable even examining it closely. But the evidence, as we are about to see, does not ask for our comfort. If the universe we inhabit emerged from a previous one, then that previous universe obeyed the same physical laws we observe today. It expanded, it aged, its stars burned through their fuel and went dark. Its galaxies slowly dispersed as the cosmic expansion continued, pulling everything apart over incomprehensible stretches of time, not millions of years, not billions, but durations so vast they dwarf any number we comfortably use. Eventually, in that earlier universe, the last remaining matter decayed. Protons broke down. The final black holes, the heaviest and most long-lived objects in the cosmos, slowly evaporated through a quantum process first described by Stephen Hawking, a gradual, particle-by-particle leaking of energy from the event horizon until, after an almost inconceivable duration, nothing solid remained. What was left at that point? Only radiation, photons and other massless particles stretching across an expanding void with no mass to mark distances, no clocks to measure time, and no structures to define scale. And this is where the mathematics takes a turn that forces a remarkable conclusion. In Einstein's general relativity, there exists a class of transformations called conformal rescalings, mathematical operations that change the size of everything in the universe uniformly without altering any of the angles or geometric relationships between objects. Shapes are preserved, structures are preserved, but absolute scale becomes meaningless. A universe in which all particles are massless, as our hypothetical far future cosmos would be, consisting entirely of radiation, is perfectly invariant under these conformal rescalings. Its equations look exactly the same whether the universe is described as vast or as infinitesimally small. Size, in that context, is not a physical fact. It is a convention with no observable consequence. This is the core of what physicist Roger Penrose calls conformal cyclic cosmology, and the implication is extraordinary. When the previous universe reached its final state, an infinite, cold, massless expanse of radiation with no meaningful sense of distance or duration, that state is mathematically indistinguishable from the dense, hot, radiation-filled singularity that characterizes the beginning of a new universe. The end and the beginning are not two separate things separated by a mysterious gap. They are the same geometric object, described from different perspectives. The death of one universe is the birth of the next, not metaphorically, but as a precise mathematical equivalence. And if this is true, the transition was not smooth. It was violent. In the final moments of the previous universe, the last black holes completed their evaporation, not quietly, but in explosive final bursts, releasing all of their accumulated mass energy in concentrated pulses of radiation. These pulses pass through the conformal boundary and emerge in our universe as intense points of energy at the moment of our Big Bang. Penrose called these energetic seeds Hawking points, concentrated focal regions, where that inherited energy left its mark on the newborn cosmos. Imagine dropping a stone into a perfectly still pond. The impact sends out ripples, concentric, circular waves spreading outward across the water's surface. A Hawking point would do something equivalent in the plasma of the early universe. Each burst of inherited energy would drive a spherical pressure wave outward through the primordial soup of particles and radiation. As our universe cooled and expanded over billions of years, those pressure waves would have left permanent thermal imprints, faint but measurable patterns in the distribution of temperature across the sky. Rings, concentric circles of slightly different temperature, stamped into the oldest light in the universe. The oldest light in the universe has a name. Scientists call it the cosmic microwave background, a faint thermal glow that fills the sky in every direction, left over from the moment our universe first became transparent to radiation, roughly 380,000 years after the Big Bang. We have mapped this light in extraordinary detail using space-based observatories. And what those maps reveal is a picture of the early universe accurate to millionths of a degree. It is the most precisely measured physical phenomenon in the history of science. Standard cosmology predicts that the temperature variations in this ancient light should follow a pattern consistent with random quantum fluctuations, statistical noise distributed in a way that can be modeled mathematically, but which contains no large-scale organized structure. No circles, no rings, no concentric patterns that repeat across the sky, just the gentle random texture of primordial uncertainty. But when Penrose and his collaborators applied statistical analysis to the actual data from these sky surveys, not theoretical predictions, not computer simulations, but the raw measured temperatures, they found something that the standard model does not predict and cannot comfortably explain. They found circles, concentric rings in the cosmic microwave background where the temperature variation is anomalously low, regions of unexpected uniformity nested inside one another, appearing across multiple datasets, and in positions that statistical chance alone cannot plausibly account for. These circles, according to the framework we have been building, are exactly what Hawking points would produce. They are the pressure wave signatures left by the explosive final evaporations of black holes from the previous cosmic era waves that propagated through the early plasma of our universe and imprinted their circular geometry on the light that has been traveling toward us ever since. They are, if this interpretation holds, the first direct observational evidence that our universe is not the first universe. They are fossils of a world that died so that ours could be born. The scientific community has responded to these claims with significant skepticism, which is appropriate and expected. Alternative explanations have been proposed. Statistical objections have been raised. The debate is active and unresolved. But the circles themselves are not in dispute, they are present in the data. What remains contested is their origin, and that contest is not yet settled. What is already clear, however, is the broader shift in understanding that this entire line of inquiry demands. We began tonight with a simple observation, the darkness of the night sky, and traced it through a chain of logical steps that dismantle the classical picture of an infinite, eternal, static universe. We found that the universe has a finite age, that time acts as the true filter between us and cosmic fire, that the beginning of our universe required extraordinary precision that cannot be dismissed as chance, and that the mathematics of general relativity points toward a cyclic structure in which universes succeed one another through conformal transitions at their boundaries. The night sky that once seemed like an empty backdrop turns out to be a window into the age and structure of the cosmos, into the thermodynamic history of everything that has ever existed, and possibly into the remnants of a reality that predates our own. The darkness is not absence, it is information. Every photon that reaches your eye carries the history of how far light has traveled and how old the universe is. And some of those photons, according to the evidence being gathered right now, may carry the echo of a world that came before ours. Step outside tonight. Look up at that black sky. And remember, what you are seeing is not nothing. You are seeing the boundary of what time has allowed light to reach. You are standing at the edge of a cosmic horizon, looking back at a history that goes deeper than any single universe. If this kind of knowledge is what you want, not comfortable summaries, but the actual structure of reality as the mathematics reveal it, then subscribe now, share this video with someone who refuses to accept easy answers, and follow along as we keep pulling on the threads that unravel everything.